In this video, I'm going to walk through a notebook slash blog post that I've written up in which I do a deep dive into RAGatouille slash ColBERT indexing. And this is so I can better understand all these different components that come into play using these libraries when you want to index documents so that you can retrieve from that collection. So the first thing I want to walk through is this high-level outline of the different methods and files that we are going to touch in this video and in this notebook. And this was both done by manual inspection, so clicking through the code base and tracking down different symbols across files. But what I also did, the main way I learned about this, and I don't think I could have done it without it, was to provide the RAGatouille and ColBERT repos as context to Claude projects and then have, very long conversations, multiple conversations, explanations as I was working this out in code. To create the context that I provided Claude project, I used Answer AI's Tools LM, which is a fantastic library where you can point it to a folder with Python files, for example, and it will create a XML style formatted document, text file, where it has different tags for documents and the source in terms of file name, and then it has the body of the file in between those document tags. I think there's document content tags. So that was a big step for me in getting over this hurdle of understanding these different elements. So let's dig into it. We're going to start with RAGatouille. That's our interface, and we load up our RAG pre-trained model, and then when we pass our pre-trained model our documents, it's going to process them by splitting them into the maximum length of chunks that we specify. It also creates some IDs for those documents, and if you provide metadata, it processes that as well. And then it calls the main function of interest for us, which is index. Now, that index function, within that index function, we're actually going to call model.index, and that goes to RAGatouille models slash colbert.py. And model.index, within that, we're going to call model index factory construct. The default type of index is the plaid index, so we're going to call plaid.construct. And within construct, we call plaid model index.build. And then inside that, we call indexer.index. Obviously, there are a lot more details that I'm kind of glossing over, and there's nuances in terms of multiprocessing and things like that throughout this pipeline that I'm not going to go into detail. But this is overall what I found to be the pipeline for RAGatouille in terms of indexing. Now, this indexer is the collection indexer that comes from the ColBERT library. So this indexer.index line in RAGatouille, I understand that to be the handoff or the connection point between the RAGatouille and the ColBERT libraries. So inside indexer.py, there is a encode function that is imported, and I should say, sorry, this is not a collection indexer, this is an indexer class. So that comes from indexer.py. I think from collection indexer, we import encode. Yeah, that's encode. And then we also import launcher. And then inside indexer.index, we pass encode to launcher. And later on, we process. And what that does is inside encode, it will run. It'll call this collection indexer.run. And that kind of initiates the entire process. We also transform the collection of documents. So from a list of strings, it creates a collection object. But the main thing about encode is it calls run, and that sets off the entire sequence of events within which indexing happens. So inside run, it calls setup, then it calls train, then index, and then finalize. Inside setup, we're basically planning the entire indexing approach. So we're going to calculate some sample token embeddings, and we're going to get those embeddings by calling collection encoder.encode passages, which eventually boils down to calling the .BERT method on our ColBERT model. Then once we have saved that plan, we're going to go into the train method, and we're going to cluster those sample token embeddings into our clusters from which we get our centroids. And then we're also going to calculate the residual between our sample token embeddings and the centroid vectors. And then we save that. And then once we have our centroids determined, we can now continue with indexing all of our token embeddings throughout all of our documents. And so we call encode passages again, but this time we don't give it our sample, we give it our full set of documents. There is a save chunk method that we're going to go into, which handles some of the intermediate artifacts that are created. We're going to use our residual codec, which handles all of the quantization, the compression and binarization of our residual vectors. And that gets saved. And then we run our final command inside of collectionindexer.run, which is collectionindexer.finalize, where we build our inverted file index, we optimize it, and this optimization is really the main difference that plaid indexing, or one of the main differences that plaid indexing introduces. So we'll see how building the IVF is going to start with a mapping, which is just a list from token embedding IDs to centroid IDs. And then we're going to optimize that by creating a mapping, so another couple of lists that maps between centroid IDs and passage IDs. And so those centroid IDs and passage IDs are then used during the retrieval search phase of RAGatouille, where we use centroids to find our top K documents. I have a video on the plaid scoring pipeline. I will link it at the end of this video. So if you're interested in that, I've done a similar deep dive walkthrough for that, and then we update some metadata. So at a high level, kind of 30,000 foot view, that's the data flow, and that's kind of the different components that are involved with indexing. All right, so that's what we're going to follow. And so if you look at the table of contents, it basically just follows everything we've done here, but it goes through it section by section. This is a bit messy, but I've tried my best to put imports in the order of use throughout the section. So you can sort of see where some of these things come from. So plaid model index comes from models.index. The collection encoder and indexer come from those respective files, and so on. I'm leaving this in here because I did set the seed. I was trying to see if setting all of these seeds will keep some of the randomness deterministic. Either I've done it wrong or it doesn't work that way, so I couldn't quite get that behavior to work, but I've kept it in here because everything is done after setting the seed. All right, so we're going to start with our source of truth. This is our ground truth, RAGatouille RAG.index. So everything that happens in RAG.index, we want to compare manually, step by step. I'm using this conditional QA corpus from the UKP Lab document-aware passage retrieval dataset collection, and I'm going to pick 1,000 passages. And here's what some of the text looks like. I'm going to use answer.ai's answer AI ColBERT small v1, and because I've been doing a lot of experiments with that. And then this is the main line that we run here to create the RAG index. And you can see some important information in here. So it's encoding our 1,000 passages. The average document length in number of tokens is about 15. It's going to create 1024 clusters and therefore centroids. And I think that's pretty much it. It shows the length of this mapping from token embeddings to passage IDs, 15198, and we're going to see that number a lot throughout this process. So kind of cool to see some of these checks, some of these values that are good checks to keep in mind as we're working through this. So what happens in the index path? So this is what gets returned by RAG.index. And if we look at inside the index path, we can see that there are a number of files that are created, either JSON files or PyTorch tensors. So what I'm going to start by doing, as you can see here on the left, is I'm going to walk through every single file, and we're just going to take a quick look at what's inside there, because as we're recreating manually the indexing process, we're going to check that the values we create somewhat closely match the values that are created by RAG.index. I couldn't get exact values. My guess is because of randomness. It could be because I did something wrong. But as long as the values were similar, I was satisfied. All right, so first thing we're going to look at is buckets, PyTorch. And we have 15 bucket cutoffs and 16 bucket weights. As we're going to look at later on, these are what are used to compress the residual vector values. And so we kind of group the vector values in these bins, and each bin gets assigned the corresponding weight. And there's some error, but that's the cost of compressing this down to more concise information. Then we have residuals, and this is 15198 by 48. 15198 is the number of tokens in the entire collection of 1000 passages. And this 48 dimension is related to the embedding dimension, the hidden dimension, or I guess the output dimension of the Answer AI ColBERT model, which is 96. And if you look at what residuals contains, it actually contains integers. Residuals is the distance between the token embeddings and the centroid vectors. So obviously these integers are not to be taken literally. It's not 30 units difference between the residuals and the centroids. That would not be a very good precision in terms of approximating our token embeddings with a centroid that's so far away. But instead, and this was one of the really cool things that I learned about in this process, was that this integer is actually a kind of proxy for two 4-bit codes that each correspond to a quantized value, which are, I believe, these values here in bucket weights. So 30 is an integer. It's an 8-bit integer. It contains two 4-bit codes, and each code corresponds to a quantized value. So each number here actually represents two float approximate values. And so there's 48 values for each token embedding. Each one of these 48 values is encoded to float values. So we're actually dealing with 96 values, which is the correct output dimension of the ColBERT model. Another star of the show, the IVF. And here we can see that it's less than our 15,198, and that's because we're going to be looking at unique passage IDs as they map to the centroids. So what this shows is that the first 8 values in the IVF, so here's 5, so 3 more. So the first 8 values in the IVF correspond to the 0th centroid ID. So this is our mapping between passage IDs and centroid IDs, and the passage IDs are the unique passage IDs that correspond to the tokens in our collection. So we're going to take a look at that in more detail as well. Here's again, we're just confirming some information, number of passages, number of embeddings, so that's a good check. The collection is a JSON file with the data set, so we can see there's 1,000 items, and here's that first document, albeit one word. Then the average residual is just a single value, and it represents the mean value of our residuals between our token embeddings and our centroids. So as you can see, the mean value is 0.015, which is, reasonable. So that makes sense that the difference between our token embeddings and the closest centroids is a fraction. This is another key component, which is docLens, where we have 1,000 values in this list, and each value represents the number of tokens in that passage ID. So the 0th passage has 4 tokens, the second passage has 20 tokens, third passage has 18 tokens, so on and so forth. And I'm just going to see here. I wonder if I can do this. I don't know if this was rewritten later on. But yeah, the sum of docLens is the number of total tokens, which is 15,198. Metadata JSON has a ton of information. These were kind of the key ones as in terms of just kind of sanity checks of number of centroids and number of token embeddings. Another key point is how small or how kind of, I don't know what the right way of talking about this is, but how strong is our compression. So we are compressing each of our full precision residual values into 4-bit floats. And, well, I shouldn't say 4-bit floats. I should say 4-bit kind of codes, and each code is going to correspond to one of the bucket weights based on the bucket cutoffs that we have kind of binned our values into. And there's a couple other kind of configuration values that are important that we see in here as well. Okay, moving on, we have centroids, which is exactly what it sounds like. These are our Answer AI ColBERT encoded centroids. These are the centroids of the clusters that are created based on the sample of token embeddings, and there's 1,024 of these centroids and 96 dimensions each. And these are full uncompressed values. These are, I don't know if this is full precision. I think it's half precision. Yeah, float 16. So, but yeah, these are not quantized. Then we have codes, which is something that's going to come up. As you can see, the length of this is 15,198, which is the number of tokens. And the values represent the centroid IDs that that token is closest to. So the 0th token embedding is nearest to the 138th centroid. Not so interesting. It just is a mapping between passage ID and the document ID, which is just a random string. And then plan.json is similar to metadata.json. So we won't go over that again. Yeah, so that's the overview of everything, of all the files that RAG.index creates. And as you can see, there's a ton of information in there. And honestly, I think without this set of files, I don't think I would have been able to check my work and understand whether or not at least I'm headed in the right direction. So very helpful to see this information to understand what's going on. All right, so now we're going to try to recreate as best as we can each of these index path elements. So the first thing we do is we want to process our collection. For that, we need some passage IDs, which are these random strings. RAGatouille uses the corpus processor, and we're going to pass it our text, our passage IDs, and the maximum chunk size in terms of number of tokens. And what we get back is a list of dictionaries where there's a document ID and then there's the content of that document. So passage and document are used interchangeably. One small thing I wanted to look at as an aside was what are the token sizes of our documents. So we use sentence splitter, which is what RAGatouille uses, and that has a token size method. So I'm going to just loop through my passages and I'm going to look at the distribution of token sizes. And on average, it's about 13 tokens, 10 to 13 tokens long. Maximum is 65. So very small size overall. So this document collection is quite small. And then we create that PID doc ID map so we can see our random UUID for that. We also reformat our text so that it's a list of strings, and that's it for that. Cool. The next part is basically a rehash of what we saw in the kind of overview. RAG.index calls model index. The model is ColBERT instance or ColBERT class. ColBERT index calls model index factory construct. That calls plaid model index construct, which then calls plaid model index.build. So that's what we're going to look at. I'm not sure what this B size is. I think it's batch size. It's 32. I think that comes into play when you do search, if I recall correctly. I don't think it came into play here. Based on the size of the collection, we're going to determine the size of our compression. And so we have a very small collection, so we're going to allow 4 bits per float. This piece was really important, getting the ColBERT config correctly. So there's a checkpoint config based on the model, and that already has a lot of the information. There's also a run config, which is needed later on to kind of instantiate some of the processes. We're going to set some more config values to make sure it matched what the RAG index settings were. And we're now at the point where we're looking at indexer.index. And inside indexer.index, launch is called, from within which the launcher instance is created with the encode function passed to it. So this part was a bit fuzzy for me. There was a lot of torches, multi-process items going on, so I wasn't 100% sure if I was following the right kind of chain of methods. But the callee in this setting is our encode function, and at some point we have this context, this run context that's created, and within which we call our encode method, we pass it the config, and we pass it our arguments, and we get a return value. So I was more focused on this piece where, okay, what is this callee? The callee is encode, and encode takes the config that we looked at. It takes our document collection. Shared list is another kind of multi-processing concept that I didn't fully understand, as well as shared queues. And then it passes it into collection indexer. So that's what we're going to look at next, and then we're eventually going to find our way to collection indexer.run. So in the init of collection indexer, we're going to cast our collection, lowercase c, which is a list, to a capital C collection object, and that has some additional attributes to it. I didn't go into detail, but something that you have to do because later on internally it calls some methods on collection. And then what we're going to do is we're going to get a collection encoder, which is based on the checkpoint as well as the config. And if we look at our checkpoint, this is just our kind of usual PyTorch model that we see, and this is our answer AI model. And I think, yeah, I didn't go into, oh, here we go. I think out features is the one we're looking at here, which is 96. But yes, I haven't looked at this in too much detail, but I wanted to print it out here for reference. Okay, so we've set up our collection indexer. We have our encoder, which is a collection encoder. So now we can go into the run method. And the first thing we do is call setup, and it calculates the plan for the whole collection. Num chunks is another one of those pieces that really didn't come into play because I'm using a very small collection, so the number of chunks is just 1 because I have 1,000 documents. The next thing that we do, that next thing that's called is sample PIDs and sample embeddings, and these sample embeddings are then later clustered to get our centroids. So again, we have 1,000 passages. This is coming from the ColBERT v2 paper. To reduce memory consumption, we apply k-means clustering to the embeddings produced by invoking our BERT encoder over only a sample of all passages proportional to the square root of the collection size. And so that's what we see here. So right now we don't know what our I guess I don't know. I guess we do know. I'm not sure why this typical doclin was used, but I think it's used as maybe an upper bound because later on we say, okay, our sample PIDs, the number of sample PIDs we're going to use is the minimum of either 1 plus this approximate value of 5542, or number of passages, which is 1,000. So we're going to use all 1,000 of ours because it's small enough. We're going to take a random sample. That doesn't matter because it's all 1,000, and we can see all of our sample PIDs were selected. So that whole process is just using their heuristic to pick the sample passage IDs that we're going to use for our planning stage. And because it's such a small collection, we're going to use all of them. Other things, I think, going in sample embeddings, I don't think this is too interesting. It creates a generator. We then iterate through that in a list comprehension, and our sample stays at 1,000 because it's so small. But here's the interesting part. So encode passages. So inside encode passages, they call checkpoint.doc from text. And inside that, we call checkpoint.doc. And then inside checkpoint.doc, we actually go to the super class. And inside that, we see that we have self.BERT. So here is our kind of normal inputs to a BERT model, to a transformer. We give input IDs, we get the attention mask, and we get back our encoded token embeddings. And then the key point here, which is a theme that is going to show up a lot, is that the output of BERT is normalized. And we'll see that in a second. So we pass our sample of passage IDs, which is all of them. We get back our embeddings, and we get back our doc lens. And our doc lens is basically a count of how many tokens there are in each passage. All of our tokens embedded into 96 dimensional space. And if we look at the norm of one of these, we can see that it's a unit vector. And this is really important because later on we use cosine similarity by just using matrix multiplication, and you can only do that if you are dealing with unit vectors. So everything we're seeing now is pretty much validated by what we saw above in our index path artifacts. So again, here's that approximately 15 tokens per document. This heuristic is calculating the number of partitions. So I think this was quite important. I didn't really think about too much about how this is behaving, but we have our number of passages, which is 1,000. We multiply that by our average doc length. So this should be 15,198. We take the square root of 15,198. We multiply by 16. We pass it through log base 2. And then we take the floor value, and that value is exponentiated. So we get 2 to that value. And that is our number of partitions. And we take the integer value of that. So I think the fact that we're doing this floor makes sure that this is going to be an integer. So the number of partitions is always going to be a power of 2, based on whatever this value is for your situation. And so I think it's important to note that we're using the length of the full collection here, not just our sample. So we're taking into consideration all of our documents. And then our average doc length estimate, that did come from our sample. It's just that in our case, the sample is the same as the full collection. So number of partitions is going to be the number of centroids. So we're going to be making 1,024 centroids. And how we're going to make that is we're going to cluster our 15,198 token embeddings into 1,024 clusters. And each cluster has a centroid, so we have 1,024 centroids. All right, so that's set up. So we have the plan. That's saved in plan.json. And then there's some other information in there as well. So now we move down to train. And train, like we do anytime we train, we're going to split it into a test and or train and validation split. This doesn't really do anything because we're using the full set of token embeddings, the 15,198. We're going to hold out 5% of it, or 50,000, whichever is smaller. And obviously in our case, 5% is smaller. So we have 759 tokens that we're going to hold out. So we have our sample, which is 15,198 minus 759. And then we have our held out set, which is our 759. So here's our training and kind of training / validation split. The next piece is we're going to use compute FICE k-means. We pass it the dimension of 96. which is, does it show it for me? Yeah, 96. We have a 1024 centroids that we want. This hyperparameter is 20, and then sample is our 95% of our collection. And this is kind of where the shared list concept comes in. Again, not fully comfortable with that, but I know we had to put it as a nested list. So it's simple as just passing these arguments to compute FICE k-means, and we get back our 1024 96-dimensional centroid vectors. Another key point, we normalize our centroids, and then we can see that it is indeed a unit vector. So this was the first time, kind of first point where we can check actual vector values. This underscore centroids is what RAG.index created, and then centroids without the underscore is what I just created. Wasn't really sure how to compare them, so I asked Claude, and we decided to do this PCA projection of centroids. Okay, I mean, it looks kind of concentrated in one area. Here's 0, here's 0.2, here's 0, here's 0.2. But I wasn't really comfortable with analyzing this, so I'll put what Claude said, but I'll just not really going to go into detail. But this is showing good structural similarity, but with expected local variations. Centroids are not identical, but they capture similar patterns in the embedding space. But yeah, I was hoping to get a more confident kind of similarity between the two, but perhaps the randomness of the train and test split during k-means computation was the difference, but I don't know, TBD. Okay, so once we have our centroids, we're going to get our residuals. So they have this residual codec where we pass our centroids, and then we compress into codes. And compress into codes, what it's going to do is basically this operation, where it's taking the centroids and it's taking the token embeddings from your held out sample, and it finds the cosine similarity between the two. It finds for each of the 759 token embeddings, it finds the index of the centroid, or the row in this case, that has the maximum cosine similarity, and that's what it returns here. So we have a tensor with 759 values, where each of these represents the centroid ID that had the maximum cosine similarity with that token embedding. So this is the 0th token embedding that had the highest cosine similarity with centroid ID 633. The 1th at index 2, index 3, index 4. So the indices of this tensor are the token embedding IDs or positions, and the values are the centroid IDs. So now that we have the centroid IDs, we're going to actually look up the centroids. So we're going to draw out those 759 96-dimensional vectors. We're going to calculate the residual between our sample and our centroids. So held out construct, reconstruct is the centroids. So our vector minus centroids is the residual. So again, that's the same shape. We're going to calculate the average residual vector that represents kind of the average difference between the token embeddings. And then we're going to calculate the average value of that average vector. And again, I didn't quite get the same exact value, but it was close enough. So yeah, still a bit of uncertainty, but I figured that, okay, this is not too far off, so I'm assuming we're going in the right direction. Okay, so we're going to keep moving along. And now we're going to get into the stage where we're going to say, okay, we have these residuals Now I want to compress them from, half precision down to 4-bit values. So how do we do that? So first we say, when you have 4 bits, how many different values does that represent? So you take 2 to the power of the number of bits you have, because each bit can either be 0 or 1. There's 4 bits, so there's 2 to the 4 possibilities of what you can represent. And so there's these 16 values that can be represented with 4 bits. So what we're going to do is we're going to find 16 equal groups in our vector that we want to compress, and that's how we're going to compress. We're going to bin them in those 16 buckets, and then we're going to assign some kind of average value to each bucket, and that's going to be our approximation for how we compress this information. So we start with making 16 kind of buckets. So here it's a bit easier to see. We go from 0 to 1 and we split it into 16 equal parts. So 0, 1/16, 2/16, 3/16, all the way up to 15/16 because we started at 0 and we have 16 values. And then how I understood the relationship between cutoffs and the weights is that the cutoffs are kind of the boundaries which are going to define our 16 buckets. And then the weights are the midpoints between each consecutive bucket. So if we look at, what is this, index 1 and index 2. So if we look at 0, 1, 2, so we look at these two values, the cutoff point, the weight is 0.1562. So it's like the midpoint of these two boundaries. And then we look at index 3 and index 4, so 0, 1, 2, 3, and 4, we get 2812. So that's kind of how I interpreted the cutoffs versus the weights for the buckets that we're going to use to compress our information. Next piece is we're going to apply these 16 buckets, these 16 quantiles, in terms of the cutoffs and the weights. We're going to apply it to our residual. And the interesting thing here is that this is a 759 by 96. So my understanding is that it applies this quantile situation to the flattened version of it, or at least visualizing it that way made some intuitive sense. So what I did is I took my residuals. So again, residuals are the difference between the actual token embeddings, the full token embeddings, and the centroids. I flattened it, and then I made a histogram where the bins are the bucket cutoffs. And you can see that this is a pretty near uniform distribution. So we can see that applying our bucket cutoffs is gonna yield a uniform distribution of values. Again, I compared my bucket cutoffs to RAG.index, and they were close-ish, not too far off, but they weren't exactly the same. So again, is this because I didn't generate the exact random split, and so the distribution was different, and so binning different distribution into 16 buckets gives you different cutoffs? I'm not sure. Same thing with the weights, close, not terribly far off, but not the same. And I think that's all I want to say about that. One thing I will say is I think this calculation that the weights are the midpoint of the cutoff, I'm not 100% sure because the numbers didn't quite check out. So if I take bucket cutoffs here, and we take these two values, and we take the midpoint, we get negative 0.027, but the bucket weights is negative 0.261. So why is that not exactly the same? Maybe it has to do with the distribution. Some of these are a little lower, some of these are a little higher, so maybe that is factored in. Yeah, I'm not sure about that. Um, so great. So now we have our buckets of how we're going to compress this information, and we're going to look at that in a little bit. All right. So now what we do is we take all of our passage token embeddings. So we take our entire collection and we pass it through encode passages, and we get our 96 dimensional vectors for our 15,198 tokens. And then we get our doc lens. So this is the number of tokens in each corresponding index, which is the passage ID. And it's actually in this save chunk method inside index saver where some of the really interesting things take place. And that happens inside our residual codec.compress. So if we look at compress, this is again from the ColBERT repo. We do the same thing we've done. We pass our embeddings and we get our centroid IDs, and then we look up the centroids, and then we subtract the centroids from our token embeddings, and we get our residuals. But this piece was a really cool piece, which is binarize. So we binarize our residuals before we store them. And that's where the compression kicks in, and that's where we save space with storage. So kind of zooming forward, also showing that our centroids and our embeddings are unit vectors. We get to this, and we have our residuals, which are the difference between the embeddings and the centroids. We get to this bucketize situation. So when we pass our residuals and our bucket cutoffs to torch.bucketize, we get back residuals that now carry different information. So if we look at the first residual vector, if we look at the first 5 values, this is now 87787. And what is that, right? Obviously, this is not the literal distance residual between the centroid and the token embedding. No, what this actually represents, if we look at the index of bucket cutoffs from 7 and 8, that's what these numbers represent. So the first value of the residual, and this is residuals underscore, so just to go back up here, maybe a ways up here. Might have to go back too far up, but yeah, I forget where. But this residual underscore is our actual, floating point values. So residual underscore is our floating point values. Residuals without the underscore is our compressed into codes values. And if we look at the actual floating point values, we have 6 eneg5, we have 0, 0, we have 1.7 eneg6, 0, and so on. And if we look at this one, this is less than 0. And so we have 8. So this is 6. This is more than 0. So we look at the 8th value in our cutoff, which is 6, 7, 8. So this value is going to be approximated as 0019. These values are zeros, so they're approximated as 0. This value is greater than 0, so it's going to be approximated as 0019. This is 0 again, so it's going to be approximated as 0, and so on and so forth. I might want to give this one quick try. I'm seeing maybe we can see some more interesting values. No, these values are not very interesting. Maybe another residual vector. Okay, that's a little more interesting. So let's see if we can look at the index of our cutoff for these guys. Yeah, I think at this point I already process this a little more later down, so we won't be able to look at that. And I don't want to redo this because I'll lose my place. But you can imagine that a value that is greater than 0019 but less than 0042. So I don't think any of these. Yeah, maybe this one. So 0037, that would be approximated as 0042. So that's, kind of how I understood this. So again, these bucket cutoffs are based on the fact that we have 4 bits that can hold 16 unique values. So we're going to group our vector into 16 different buckets, and the cutoffs are going to be the points where we have equal values in each bucket, and that's what it happens to be for this set of residuals. Cool. All right, so we look at the minimum value of residuals, and the maximum at this point is 0 to 15. So those are our 16 indices that correspond to our 16 possible bucket cutoffs. And again, the values of residuals are now the ID, the indices of the buckets that the residual values fall into. All right, so we have now IDs of our bucket cutoffs. Let's see how we can continue to compress this down further. So we're going to expand our residuals to hold 4 bits. So we're going to have all of our tokens, 96-dimensional encoding space, and we're going to have 4 bits. Here are the possible 4 bits that we have. 0, 1, 2, 3. This piece I didn't fully understand, to be honest. So this is something that this operator and this operator, these are things that I need to look into. But where we get down to eventually is that instead of the bucket cutoff index, we now have a 4-bit value that corresponds to whatever that particular cutoff / weight value was. So 0001. So this is a 4-bit value. 1110, another 4-bit value. Okay. So the next few lines of code, we're going to go based on the result, where this pack bits operation comes into play. And again, don't understand the full details of this, but what I do understand is that we went from a 15198 by 96 by 4 down to 15198 by 48. And if we look at the values, we have now these integers that we saw early on when we were looking at the outputs, the artifacts of RAG.index. And if we take this first value, which is the integer 30, and we convert it to binary, we get 000 11110. Now, that is interesting because if we cut this into 2 pieces, we see 0001 and 1110, and that is exactly what we have here. 0001 1110, right? 0001, whoops, 1, and then 1110. So we have gone from half precision to let's see. So half precision. We then went to integers that represent each bucket cutoff. We converted those integers, those buckets, to their binary value because there's 16 integers 0 to 15, and each of them have a 4-bit value that represents that. That we combined 2 pairs of 4-bit values at a time to create an 8-bit, which we can see here, uint8, to create an 8-bit integer. So we cut the values in half. So now instead of floating point 16, 96 floating point 16 values, we now have 48 integer 8-bit values. So that is how the compression takes place. And if we would have had a larger collection size that we were trying to index, ColBERT would have automatically picked, 2 bits or 1 bit to compress it down even more. So again, lots of details that I did not go into. So there's a lot of things that I don't fully yet understand about quantization and binarization, but this was the first time I really understood how this sort of compression takes place. And, thanks to the accessibility of the ColBERT repo for allowing me to kind of interface with these. Okay, and so this would be what is in our 0.residuals.pt. All right, so we're getting close to the finish line. Next we're going to build our actual index. And we start out with codes. So we're going to have to backtrack a bit to remember what codes were. So codes is our 15,198 tensor, where the indices are the token embedding IDs and the values are the centroid IDs. And so we can see that deconstructed down here. So the indices gets turned into IVF, the values turns into values. So IVF is now the indices of the token embedding IDs. Why are we starting at 936 and not 0? Well, that's because we sorted our codes first by values. So we sorted by the centroid ID. And when you sort by centroid ID, the first token embedding ID that corresponds to the first 0th centroid ID occurrence is token embedding position 936. So the 936, well, 937th because we count from 0, but the 936th token embedding is closest to the 0th centroid. So that's what we're looking at here. And again, cannot emphasize enough, looking at the shapes of these tensors was like the only reason I was able to keep track of what is going on. Okay, so what do we do next? We take those values and then we throw it into bin count and it gives back our IVF lengths. So what this means is that how many tokens are there for the 0th centroid? There's 10. What about centroid ID 1? That has 11 tokens corresponding to it. Centroid ID 2 has 17. So if you look at here, there's 10 zeros, then there's 11 ones, and there's 17 twos, and so on and so forth. So IVF lengths is the count of tokens per centroid ID. And if we sum that, we get the total number of tokens. So this IVF lengths and IVF is a, combined, it maps token embedding IDs to centroid IDs. All right, now comes the kind of climax of plaid indexing. So we're going to now map the passage IDs to the centroid IDs because there's fewer passages than tokens. So if we can map passage IDs to centroid IDs, we're dealing with fewer numbers. We're dealing with fewer objects that we have to store in intermediate memory as we're retrieving them. And so this optimization is really the plaid optimization, or at least that's how I'm understanding it. All right, so total number of embeddings, we've seen this number before. There's 1,000 documents. So we're going to instantiate an empty mapping between token embedding IDs and passage IDs. So we create a emb to PID of zeros, and there's 15,198. Now, this part is important, so I'm going to take my time to go through here. We have this offset doc lens that starts at 0. We're going to enumerate doc lens. So if we look at doc lens, there's 1,000 of them. The index is the passage ID, so 0, 1, 2, 3, up to 999. And then the value in doc lens is the number of tokens in that document. So emb to PID we're going to start from 0 to 0 plus, I think it was 4 was the first number. So for the first 4 documents, for the first 4 tokens, we have PID 0. And then we move our offset by the number of tokens, and then we go on to the next PID and D length. And then we have that sliding window, and we keep adding the PIDs, however D length number of PIDs for every value in doclens as we go through all 1,000 passages. So we still end up with 15,198. If we look at the first 50 values, we can see that the first 4 tokens correspond to the first passage. The next 20 correspond to the next passage, and so on and so forth. So we now have a mapping between token embedding IDs and passage IDs. So I'm just going to read this out. Recall that IVF contained as values the token embedding IDs, so here's that 936, which are the indices of M2 PID. So 15,000, excuse me, 15,198. We have the indices as a list here, and we have indices here implicitly, right? So index 1 or 0, 1, 2, 3, 4, all the way up to 15,197. So the values of M2 PID are passage IDs, right? So 0, 1, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, 4, 4, 4, 4, 4, 4, so on. So if we index into this M2 PID with our IVF, so with a list of basically indices that we want to index into, it's going to pull out the passage IDs corresponding to these tokens. So that's what happens here. We take our IVF, which is our token indices that are based on the sorted centroid IDs, and then we're going to pluck out the document IDs that they correspond to inside M2 PID. So we still have 15,198, but now we have document IDs. So the first token embedding corresponding to the centroid ID of 0 corresponds to a passage ID of 55. The second embedding, token embedding that corresponds to centroid ID 0 corresponds to passage ID 69. The third one to passage ID 143, so on and so forth. The very last token embedding corresponds to passage ID 800, and it corresponds to centroid ID 1023. So in this way, we have a mapping from document IDs or passage IDs to token embedding IDs to centroid IDs. So just reading that again, new IVF is a mapping from its indices, the token embeddings, to values, passage IDs, which now is aligned to the IVF lengths tensor, which contains number of tokens per centroid ID, which came from values. So a little confusing, but I find that this is easier to look at here. Okay, so what we're going to do now is we're going to save some space by getting the unique passage IDs per centroid. So unique PIDs per centroid is an empty list. Our new IVF lengths is an empty list. Our offset starts at 0, and we're going to iterate through our IVF lengths. So if we recall, IVF lengths is the number of tokens per centroid ID. So centroid 0 corresponds to 10 tokens, or we could think of it as the first 10 values. And so we're going to take the first 10 values in terms of our passage IDs, which is what we're doing here. So we get our passage IDs, we index into our new IVF, which is this guy. So we get the first 10 values. Those are the passage IDs that correspond to the 0th centroid. we're going to get the unique passage IDs, and then we're going to append it to unique PIDs per centroid. And then to the new IVF lengths, we're going to append basically the number of passage IDs. So, let's say there were 10 passage IDs in here, but, let's say there were 5 unique ones. These are not real values. We would have all 5 PIDs here, and then we would have the number 5 appended to this new IVF lengths. And the indices of new IVF lengths is the centroid ID, and the value is the number of passage IDs. And then unique PIDs per centroid has the actual 5 passage IDs, so 55, 69, 143, whatever. We increment our offset, and we go to the next centroid's number of tokens, which corresponds now to number of passage IDs in new IVF. So we keep going through that. The unique PIDs per centroid is what becomes our new IVF. Unfortunately, this is new _IVF, but our final IVF is our unique PIDs per centroid, and our final IVF lengths is our is this correct? That doesn't seem... Yeah, I don't think that's correct. So let's take a minute here. Let me actually, so this is optimize IVF. So I was not planning to do this live, but that comes with it. So we have original IVF lengths. I probably should have kept that nomenclature. Here's IVF lengths. So tensor IVF lengths, IVF. Okay, yeah, so no, that's not right. So this should be that line that we looked at here is actually just converting this into a tensor. So this should be new IVF lengths. It'll still be the same shape because it's a 1024, but it has now the number of unique PIDs, not the number of tokens. So if we look at the number of unique passage IDs, we actually have 11,593, which is about 4,000-ish less than the number of tokens, and that's because we have, for a given centroid, we could have multiple tokens from the same passage ID, and we're taking the unique passage IDs here. But the key thing is that in our new IVF lengths, we have 10 passage IDs. So we look at our IVF. Okay, what are the 10 passage IDs? Okay, those are the passage IDs that have token embeddings that are closest to the 0th centroid. So that's how this mapping works. It took me a minute to wrap my head around it. I'll probably forget it in a couple days, so I'll probably have to revisit this. Cool. And then it's stored in ivf.pid.pt, and then it updates some metadata. And at least for the intents and purposes of this indexing deep dive, that is the indexing process in RAGatouille and ColBERT. So final thoughts, obviously lots of details that I didn't fully explain. There were some operators related to binary values that I didn't understand. I wasn't able to replicate some of the indexing artifacts, my residuals, my centroids, my average residual mean. They were not exactly the same as RAG.index. Was that because randomness was at play and I used a different train test split for my compute k-means function? Was that because there was a bug in my code? I'm not sure. That would be... I don't know if it would be an order of magnitude harder to figure out, but I think it would certainly be its own exercise to figure out. Again, I use Answer AI's tools LM to create context from the RAGatouille and ColBERT repos. So I highly recommend that. Feed it to Claude project and go to town. You know, it'll have a lot of context, and it'll be structured, and it does a great job of summarizing that information and pointing you at which file and which line you should look at. Uh, and of course, there was also a lot of hours I've looked at this code base now, because I've done the plaid scoring pipeline walkthrough. I've done the indexing walkthrough. I've done some memory profiling for RAGatouille and ColBERT, which you can find a blog post about. And so at this point, I'm starting to wrap my head around this. I'm starting to feel comfortable around what's going on. Obviously, lots more to learn, lots more to figure out. So thank you for watching this video, and I will see you next time.